Good evening and welcome to the Autonomous Systems module. So today we are going to discuss a new topic of quaternions. So this is the outline. I will give you a brief introduction to quaternions. Then we will try to figure out the connection between rotations and complex numbers. And then we'll discuss quaternions in more detail. Afterwards, we will have a look at quaternion algebra, and then we will see how we can use quaternions as a rotational operation, and we'll also see the connection between the quaternion and rotation matrices. Right. Now, we discussed about how to represent a orientation between two rigid objects when we did the IMU theory lecture. So we basically used rotational matrices to establish the relative orientation between two objects. So in that, we also discussed some parameterizations like Euler angles. So when we are using Euler angles, we are basically using the current frame of the object, and we do certain orientation one after the other. So if we think about Z, Y, X Euler angles, as you can see here, we will first do a rotation phi about z-axis, and then the rigid body will come to a certain orientation, and we take the new y-axis of that object and do a rotation. So here you can see we are not changing the y-axis, therefore this remains same, but x and z will change. So this is that rotation matrix. This is a post multiplication, as you can remember, because we are using the current axes of the object. And finally, we do a rotation about its new x-axis. So you can see the x-axis remains same, and the other two axes will change, right? So this product of these three matrices will give you a rotation matrix of the final orientation of the rigid body, right? This is like a standard form we usually encounter. And so when we give those three angles, let's say there is a airplane, and we have different mechanisms to make rotations about basic axes, right? X, Y, Z, right? So once we go through such rotations, we will finally come up with this particular rotation, and you just have to substitute these three angles, phi, theta, and psi, to figure out all the 9 entries of the rotation matrix. Now, if you think about the inverse problem, let's say we want to achieve a certain rotation, right? So we know from the beginning what the rotation matrix is. So there is a particular rotation that we want to achieve. And in the inverse problem, we will figure out what are the three Euler angles we have to give one after the other to finally achieve this, right? So from looking at this rotation matrix, you can figure that out by specifically looking at these two elements as well as these two elements. So you can see cos theta is same, right? Here and here. So therefore we have a sine psi and cos psi. So we can make use of these two elements to figure out what is that psi angle. And in the same way, if we look at these two, cos theta is same. So from these two elements, we can figure out what's the phi angle. And here, theta is nicely isolated. So we can use this to find out theta. So we can extract the three angles given a rotation matrix, right? So this is how we do that. We can use tan inverse function for these guys, as well as since we also want to find the quadrant of the angle, we don't straight or directly use sine theta, but maybe as you can see here, we can make use of this element plus these two elements also, because here we have cos theta part as well, right? So by doing that, we can figure out the triangle. Now, here is a question. So what happens if this theta, this guy, is 90 degrees? So you can see if theta is 90 degrees, so this cos theta will become 0. So this is 0, this is 0, this becomes 0, and this becomes 0, right? So these elements all become 0. Therefore, we will not be able to find now this is like 0 over 0 kind of thing, right? These two, both the elements are 0. So this is also both the elements are 0. So we will not be able to figure out the rho and the u, or this phi and psi. So that is a problem. So this is a special case, or we call it as a singular condition, right? So if that happens, right, we are unable to figure out these angles, right? So this we call as the gimbal lock problem, right? So given let's say a particular rotation matrix, so let's say we have a final rotation matrix given by 0, 0, minus 1, 0, 1, 0, 1, 0, 0. So these guys are 0, these guys are 0. So we can come to this final orientation by infinitely many ways, right? Therefore, we cannot really figure out the rho and u angle. So here you can see this second rotation is 90 degrees pitch. This is 90 degrees pitch, but these two can be anything, right? The combinations can be anything, right? So infinite number of solutions to the Euler sequence is present, right? So this is again such singular situation, right? So let me show you what happens in such scenario, which we call as the gimbal lock. So we basically lose 1 degree of freedom in a, if you look at this particular if you look at this three gimbal mechanism, right? So you have this yaw, you have this pitch, and then you have this roll, right? So you can have any arbitrary orientation by moving these gimbals, but in this particular thing where pitch is 90, now you can see two degrees of freedoms are aligned to give you just 1 degree of freedom, right? So when the pitch is 9, so that's what happens in this singular configuration. Okay, so therefore Euler angles can be problematic in certain scenarios. Only when, if we go like come across 90 pitch angle, but as you can see, maybe for a airplane we might not go straight up, right, like a 90-degree pitch, so we might not come across that. But in other situations we may encounter the gimbal lock problem, where our algorithms and mechanisms can get stuck, right? So such problems exist in Euler. So that's where this new representation called the Quaternion representation can become handy. So this is an alternative representations for rotation, and it avoids the gimbal lock problem, and it is simpler to compose when compared to Euler angles. And if you compare them with rotation matrices, they are compact because rotation matrices have 9 elements to deal with, but here in the quaternions, today you will see we are only dealing with 4 elements. So that's how this quad part comes in, right? Like we have 4 elements only. So it's a more compact representation, and it's also numerically stable and more efficient to calculate as well, right? So that's basically a overview or like a motivation to use a different kind of representation. So now let's move on with the remainder of the lecture. Right. First of all, we have to observe that there is a certain connection between rotations and complex numbers. Let's see what it is. Right. So I am not going into details of complex numbers. I hope you are familiar with them, maybe even from your A levels, where you started learning complex numbers. So you know how to add and subtract them, and you know how to multiply them, right? And when we encounter I squared, that would be replaced by a minus sign, right? And we also know how to do division of complex numbers, right? Okay, so we say that complex numbers are a field because they are closed under addition, multiplication, subtraction, and division. So what it means by closed is if you take two complex numbers and add them together, the result would be again a complex number. If you take two complex numbers, multiply them together, and then the product will also be another complex number, and the same goes for subtraction and division, right? So when closed under all these four operations, we call it as a field, right? So complex numbers have field properties. Okay, now complex numbers, we know another way of representing complex numbers, which is the polar representation, right? So we have a magnitude and argument for a given complex number like this, and we know how to calculate the argument theta by taking these two elements a and b. Okay, and the addition can also done in the polar representation using the parallelogram law, right? And when it comes to multiplication, So when the complex numbers are represented in polar form, we can find the magnitude of the product of the two complex numbers given by the product of the magnitudes, and the argument is the sum of the arguments or the sum of the angles, right? I think these are familiar territory for you. And if you represent a complex number in this particular format, I hope you have come across the Euler formula. So in Euler formula, we can represent them using this exponential form, right? E to the power I alpha. Euler's formula. So in that, we can just figure out what we get when we multiply them using this particular form, right? We have R1 cos alpha sin alpha for the Z1, and for the Z2 we have R2 cos beta plus I sin beta, and if you do the calculations you will end up with this, right, where you can see the arguments are added and the magnitudes are the product of the individual magnitudes, and again it can be given in the Euler formula like this as well, right? And now if we limit ourselves to uh, complex numbers having magnitude 1, that is, if R1 equals 1 and R2 equals 1, right, then we can see a special property. So the product or the multiplication of the two complex numbers is actually accounting for rotation in the plane, right? So you can see these two guys are 1, and if we have a certain let's say complex number, and if you multiply it with another complex number having a magnitude of 1, it's like that complex number is rotated by the angles given, right? So here you can see it clearly. Let's say this is our complex number x, right? And if you take another complex number z having unit magnitude, and if I apply this z on x, or basically if you take this particular product, right, z into x, you see that the resultant, this guy y, is like this particular complex number rotated by theta amount, where theta comes from this operator z, right? So if you have complex numbers of unit magnitude and if you apply it on a vector like this, you can basically achieve rotation in the plane. So that's the connection I want to establish, which I think you already know, right? So the vector x can be rotated by a unit complex number, and the magnitude will not change, right? And this angle, the amount, the rotated amount actually comes from z, the inherent angle of z. Okay, so what you need to know is you can make use of a unit complex number to achieve rotation. Okay, so if you think more on this, or maybe that's what inspired Sir William Rowan Hamilton back in 1800s, right? That's what inspired him to think about, okay, if a complex number which we know can do rotation in the plane, then maybe in a similar manner, we should be able to achieve rotation in 3D. Maybe not the same complex number, but maybe a very, very complex number, right? So the complex number is already complex, that we know. So how about we make it more complicated and call it as a hypercomplex number, and we apply that hypercomplex number to a vector, then maybe we should be able to achieve three-dimensional rotation, not just planar rotation like this. We should be able to somehow take a vector and get it rotated in 3D. Okay, so he came up with these properties. These are called Hamilton special uh, properties. And so we already know I squared equals -1. So he proposed, okay, there should be two more dimensions into complex numbers where we have j-axis and a k-axis. So these are again complex numbers in different dimensions, right? And if you think about ijk product, it would also give you a -1, right? So this is how quaternions were born, and they have rank 4, or it has 4 elements, right? And these quaternions are also having field properties, except for the commutative law for multiplication. So that means I think you know what commutative law, right? So if you take a quaternion Q1 times Q2, this is not equal to Q2 times Q1. So this is basically same as rotation matrices. We know that the order is important, right? Okay, so this is Sir Hamilton. He's from Ireland, and it was said that when he was going home thinking about this particular concept, he came up with these so-called Hamilton special products, and he quickly wrote them somewhere in this particular bridge. So now it's called Hamilton Bridge, and here you can see there is a plaque, right? He says here as he walked by on the 16th of October 1843. In a flash of a genius, discovered the fundamental formula for quaternions. So these are the products he wrote down on the stone of the bridge, right? Okay, so I think now we are also curious to know what these quaternions are. So let's dive in to the. So first of all, I will give you some definitions. So definitions are okay. Someone says so we just accept it, right? So we denote quaternions. We can denote them by lowercase letter. Let's say P, Q, R. So these are quaternions. And if you take a quaternion, it has 4 elements. Okay, so they are simply real numbers or scalars, right? And now we are dealing with quaternions as well as ordinary vectors in 3D, right? Because our ultimate goal is like, okay, there is a certain vector v, right? And I apply a quaternion, so similar to a rotation matrix we learned. I apply a quaternion to this particular vector, and I should be able to maybe get a rotated vector in 3D, right? So that's what we want to achieve through the quaternion. So since we are dealing with ordinary vectors, also quaternions, let's denote the ordinary vectors by maybe bold faced letters. Okay. And the standard orthonormal basis for R3 we already know, IJK. Now this is a little bit tricky because for complex numbers also we have I, and for ordinary vectors also we have IJK, which are given by these three orthonormal bases, right? So they will overlap here and there, but don't worry too much about it. Let's see how it goes. And this is alternative we can use to represent quaternion. So as I said, maybe we can have these four numbers like this, or else we can divide the quaternions into two parts. So there is a scalar part. This is Q naught is the scalar part, and we have a vector part. Okay, so this is upright Q. So you can see here we have the vector part. So it's like a vector that comes in this form, or as I said before, these are like coming from the hypercomplex numbers, right? So you have three dimensions of complex numbers, and it also act like a certain direction of vector, right? Okay. I hope you are with me so far, right? We still didn't go into much of the complicated details, right? So we have a quaternion. It has a scalar part. And it has a vector part. So this is like this hyper complex part, right? So you can see that quaternions are mathematically like strange objects, as I have mentioned here, because you have a scalar and also a vector part combined together, right? Therefore, we have to formulate some rules how to deal with quaternion manipulation. So you already know real numbers, you know integers, right? Likewise, you know different stuff in mathematics. So now you come across this new object called quaternions. So similar to integers or similar to real numbers, fractions likewise, let's establish some rules how to deal with. Okay, and that's what we call as the quaternion algebra. So it's just a set of rules that we will use to deal with the quaternions, right? So to start off, we can say the two quaternions P and Q are equal if these individual, like these corresponding elements are equal. Okay, so P naught equals Q naught, P1 equals Q1, likewise, all the elements are equal. Therefore, the two quaternions are equal. So here I'm one by one telling you some rules and how to deal with them. Right? Then when it comes to sum of two quaternions, it's again pretty much same as other algebra. We take the summation of the corresponding elements, right? So this is the like the scalar part. Here we have the I part, J part, K part, right? So we just take the summation of them. And this result is also a quaternion because it's closed under addition. Okay. And we also define a zero quaternion. So zero quaternion is just every element is zero. So we have 0 plus I0, J0, K0. Okay, it's the zero quaternion. And we have additive inverse that is called minus q, and all the elements will become minus, right? So say it's q1, q2, q3, simple as that. Okay, so if I add this guy to q, if I do the addition of this and that, I will get the zero quotient. Okay, and the addition of quaternions are associative and commutative. I hope you know what this means, right, when it comes to addition. So this is like a plus b equals b plus a. This is commutative, and I can have a plus b plus c equals a plus b plus c. So this is associative, right? So that's same for quaternions as well, right? Now, if you move on to the multiplication, right? So the product with a scalar c, right? It's simple as just simply multiplying these individual elements by c. Simple as that. Okay, that's a product with a scale. Now, this is the little bit involved thing, that is, if you want to take the product of two quaternions, right? When we do that, so here we have a simple quaternion like this. Now I want to multiply P and Q. Okay, so in order to do that, now we need these Hamilton special products, because you can see, let me write it here quickly. So P as P naught by E1, E3, and Q as Q naught, Q1, Q2, and Q3. So when you do the product, you can see you have to multiply I times j, I times k, k times I, likewise. Those products are needed. And now we need these Hamilton special products. So that's how he defined it, and it seems to work. Okay, and so there is some cyclic way of achieving these guys, right? So I times j, we get k, and I think you have also learned this when you do the cross products also, right? We will make use of these elements and try to figure out how we can do the product of two quaternions. So let me show what happens. So here you take P naught and multiply it by Q naught, and P naught times IQ1, P naught times JQ2. Likewise, we have all these elements over here. Okay, and when you come across I squared, you will put a minus 1. I times j, you will replace this with a k, and I times k is minus j, likewise. Okay, when we use the Hamilton special products, we will be able to simplify the product of two quaternions into this. Okay, you just don't have to worry what these elements are at this particular moment. Just check whether these guys are properly substituted by these products. Okay, so we get this particular answer, and we will not stop there. We can actually identify some more patterns in this one to simplify this product even further. So for the simplification, we will use things like this. So I hope you know the scalar product for vectors, right? If you have a dot b, you have a1 b1 a plus a2 b2 plus a3 b3 likewise. So that is our scalar product. And for the cross product, a cross b, you have ijk a1 a2 a3, and you take this guy and you get this answer. Now when you look at this particular answer, you can actually see some of these guys are inside, right? For example, this guy over here. So this is like p1 dot q. Okay, so as I said before, of course we are dealing with hyper complex numbers, but at the same time we can think of them as maybe a regular vector as well. That's why I'm going to use these dot products and so on, right? So I will replace this guy with the dot product, and here you can see p naught times, this is the vector part of q, and this is q naught times vector part of p. And this guy is actually like this. So it's basically the cross product between quaternion and the P and Q. Okay, so when I applied all these stuff, now I can further simplify the product or the multiplication of two quaternions into this one. Okay, so you take the two scalars, multiply them, and you subtract the dot product. So this is also a scalar part. So this whole thing is the scalar part, the new scalar part. And these are all vector parts, right? This is vector part times scalar part of p likewise. And finally we have the cross product. Okay. Maybe we can do a simple example and be familiar with quaternion multiplication. Let's say we are given with this quaternion, so there is a scalar and a vector part, and here again we have a scalar and a vector part, right? When I do the multiplication, of course you can just multiply them one by one from scratch, or else you can just make use of this guy and find the answer as well. Whatever is simpler, you can use it, right? So if I use this formula, in this case, we need p dot q, right? So p dot q, so I'm actually talking about this vector part dot this vector part. Okay, so I can just find out 1 times minus 1 minus 2 times plus 2 here, and 1 times 3. So I get this answer. So this minus 2 is this, right? Then I also need the cross product. So I have ijk. Then I have 1 minus 2 plus 1, this row. And then minus 1, 2, and 3, this row. And I can again find this answer. And when I put all these together for this formula, I will get a certain answer, right? So this is the quaternion product of P and Q. Okay, so you can see again you are getting another quaternion. There is a scalar and there is a vector. Now, up until now, you just have some abstract object called quaternion, and I told you some rules how to deal with the quaternions, and you can now do certain operations and get some answers. Still, we don't know what a quaternion does and what's the physical representation. So you just have to wait a little bit longer, right? We'll go through these guys and figure out all the rules, and then I think we will be ready to move on to really find out what a quaternion does. Okay, so the next part is there is another way to do the quaternion multiplication. That's basically by using matrices, right? So previously I had this answer, and what I did was I grouped them in a certain manner, right? This is the dot product, and this is the uh, cross product, and so on. But another way to group them is maybe, okay, I group using I terms, j terms, and k terms, right? All I take all the I terms together, all the j terms together, and if I do that, uh, so this is the scalar part. That is again same as before, but if I group the I parts together, I have P naught Q1, Q naught P1 likewise. So this is the I part, this is the J part, and this is the K part. Right? So I can write them as a matrix vector product, right? So this is my second quaternion elements. I wrote them as some vector, and based by looking at these guys, I can come up with this particular matrix. So there is a special pattern you may identify: P3, P2, and P1, P3. Likewise, there is a pattern. So this is generated by taking the elements of this P code, right? P naught, P1, P2, P3. I put it in a special pattern, and you get the matrix vector product. And again, you can find out the multiplication as well. Okay, so that is also another way of doing the multiplication. Or as I showed before, this is the other formula you can use to find the product of quarter. Okay, right. And let me give you some more of some useful identities. So when it comes to multiplication, there is a multiplicative identity, right? So in real numbers, you know that is 1, right? So if you have a certain number x, the multiplicative identity is simply 1. So similarly, when it comes to quaternions, the multiplicative identity is 1 plus 0. So the vector part is 0 in this case, right? So if I take this guy and multiply with another quaternion, you know the answer would be again same, right? This is the multiplicative identity, right? It's just the scalar one. And multiplication of quaternions are associative. It is P times QR is equal to P times QR. So this is associativity, and it is also distributive of addition, that is P times Q plus R is equal to PQ plus P. That property is also okay. So I'm just going through the rules in the quaternion algebra. Okay, just accept it for now, and everything would be helpful little later, right? Then we can also define something called the complex conjugate. I think you know what it is, right? When it comes to complex numbers, if you have, let's say, a plus ib, the complex conjugate is a minus ib, right? So similarly, for the quaternions, we can define complex conjugate. So in that, we give a asterisk, so star, q star is just the minus of this one, right? Similar to the complex conjugate of complex numbers we know, right? So the vector part would become minus, as you can see, right? And this is a property P Oh, yeah, it's already there. So if you take the complex conjugate of a product of quaternions, this particular property holds. So it's like uh, similar to maybe the transpose of matrices. Remember, if you have A, B transpose, this is equal to B transpose, C transpose. So in the same manner, for the quaternions also, we have the complex conjugate of the product of quaternions would be Q star P star, right? And next is if you add Q and Q star, then of course you know that these two will disappear and it will give you just 2Q, right? The scale part, right? Maybe we go to them as well. Then we can also define a norm for a quaternion, right? So it's like the magnitude of the quaternion, right? And it's given or defined by this one, right? The square root of q conjugate times q, and it's also same as square root of q times q conjugate also. Okay, so this is actually giving like a magnitude for a quaternion. And if I look at the square of the norm, then I have q conjugate. So this is q conjugate, and this is just q, right? And the square root will disappear, right? And this is basically multiplication of two quaternions, right? Just like P and Q. So we now know the formula for the multiplication of two quaternions. So I can just make use of that to find the answer for this, right? So I get, okay, quickly write it down. So this would be equal to Q naught squared. So that comes from this part. Okay. And then I have minus P dot Q is P dot Q naught times Q times Q naught. And finally I have Q minus Q cross Q. Okay. I just substituted the values here, right? So you can see these two guys disappear. And what about this one? So these are like parallel vectors, right? Qn minus q. And if you take the cross product of parallel vectors, that would also disappear. Okay, so we square plus q uh, like the dot product of the vector part. So this is simply q1 squared, q squared, and q3 squared. Or I can simply write it this. Okay, so I just take the four elements and get the summation of the squared values. Okay, that's how we define the norm of a quotient, right? And if we restrict ourselves to unit quaternions, that means your norm is 1. Okay, now unit quaternions will be import, just similar to what I introduced for the usual complex numbers here. You can see the unit complex number was special in this case. That acted as a rotational operator for x, right? So the amount to rotate came from this, and because it was a unit complex number, the magnitude of x did not change, right? So that's basically what we need in a rotational operator. The magnitude should not change, and the amount to be rotated should come from this operator that we are applying, right? So the amount to be rotated, that information should be in Z. Okay, so similarly, now if I come back, still we don't know what the quaternion does, right? We are just going through some rules. We are just establishing some rules, but in a similar manner, the quaternions with unit norm is what we would be interested in. That's why I told you as a head start for you guys, right? So we will be mainly working with unit quaternions, and that's what would actually help us rotate a certain 3D vector, okay? By preserving its magnitude. Okay, now if we further look at the norm of the product of two quaternions, as it says here, it will be equal to the product of individual norms, right? Maybe I can quickly write that also here. So I have P and Q, and I want to find the norm of the product, right? So I can just write it like this. So here, this is how it was defined, right? The square root of Q conjugate Q. So since we are talking about the square, we can just write PQ conjugate P. Okay. This is the norm. So this would be equal to Q conjugate P conjugate times PQ. And P conjugate P is actually equal to norm of P, right? Times Q conjugate and Q. So norm of Q is scalar, so maybe we can just bring that to the front. Okay, so that could be this guy times conjugate Q. This is, so basically your answer would be the norm of the product would be equal to the product of the norms, right? Q times. As I said before, if we are dealing with unit quaternions, this would be 1. This would also be 1. Therefore, this would be 1 as well. Okay, so the product of two unit quaternions will also be a unit quaternion. Right. One more thing before we move on to the graphical representation of quaternions, that is the quaternion inverse. Okay, let's see what it is, because just like the matrix inverse, this is going to be very useful. Okay, so we define the quaternion inverse as Q to the power -1, and when we do the multiplication, it should give you 1. Okay, so this means, okay, Q inverse Q is equal to 1, and another one I can write is Q inverse equal 1. And if I multiply this with Q conjugate, also, and I can do the same for these equations. Now, this guy is actually the norm, right? The scale that tells you the magnitude, right? So from both these two equations, I can write Q inverse is equal to, so this guy can go to this side, right? Because it's just a scale, right? I can just not worry about the product or the multiplication because it's just a scalar. I can put it this side, and same for this one as well. Therefore, this would be equal to Q conjugate. These equations, I get the same thing, right? So that's the inverse of a quaternion is equal to Q conjugate divided by the norm of the part. As mentioned before, if we are dealing with unit quaternions, this guy would be 1, right? The norm. And then you have a very important result. So the inverse quaternion is simply equal to the conjugate, right? So isn't that very convenient for us? So we have some Q naught plus I Q1. Okay. So later I will tell you this is a rotational operator, but still we didn't say that. So later, if you want to find Q inverse, it's very simple. It could be simply minus of the vector part, right? That's why I told you before that the very efficient methods to do like inverse rotation and so on. So this basically, I think you remember, this is analogous to uh, integration matrix, right? That was also easy to calculate. Inverse rotation is equal to the transpose, if you can remember. So this is a special property of rotation matrix. So when it comes to quaternions, it's even further simplified, right? You just take the conjugate of that operator. Okay, right. So it's about the quaternion algebra. So I introduced you to some abstract mathematical concept, and I told you some rules how to deal with them, right? So it's, if you go back to your kindergarten days, you were introduced with maybe integers, 1, 2, 3, 4, and we were told some rules to how to deal with these integers. Okay, v1 plus 2 equals 3, so we established a certain set of rules. So similar to that, I introduced something called quaternion, some strange mathematical object which has a scalar part and a vector part, right? So this is a vector part. We call it as a hyper complex number. So it is like a complex number in 3 dimensions. So it's basically like a vector, no problem treating that as a vector, because we already did, right? There were like ij, k parts, and we did dot products, cross products for this hyper complex guy also, right? So these are some rules we established. Okay, now having known these rules, now we should look at what exactly uh, is achieved using the quaternion. What's the physical, the practical implications of the quaternion in terms of rotations, right? So let's see what it does. Okay. So what we need to do is, okay, there is this object called quaternion in R4. That is, there are 4 elements, right? So we want to use this quaternion and operate it on a vector in R3. It is like 3-dimensional vector, right? X, Y, Z. Okay, I want to apply the quaternion on a vector and see what happens. Okay, so if we want to do that, like apples and oranges, right? This is something, and this is another thing, right? So if you want to apply this, maybe we want to make them similar, right? So what I can do is I can take a vector in R3 and let's represent the usual vector as a quaternion where the real part is 0. Okay, so I just take a 3D vector like this, which has x, y, z. Now I want to represent this as a quaternion. So the simple way I can do that is, okay, this has 4 elements. Let's make the scalar part 0. And then for the vector parts, let's take these 3 elements and put it over there. Now it becomes a quaternion, right? In fact, quaternions are called pure quaternions because there is no scalar part, right? The scalar part is 0, right? And interestingly, there is a one-to-one correspondence between such vectors in 3D and the pure quaternions. Okay, so if you look at this diagram, so these are vectors in R3. So there are 3 elements, right? The usual vectors we know. And there is this quaternion space which has 4 elements. Okay, so here I can have maybe a sub category of R4 called pure quaternions, where the ones that have the scalar part 0. And previously we also talked about unit quaternions also, right? That means the magnitude of the quaternions is 1. So there can be another like a subpart, but for the time being, let's just think about, okay, the pure quaternions. So what I told you here is, okay, I want to apply a quaternion on a vector so that I can maybe get this vector rotated, okay, as a rotational operator. But this is coming from different domain, and this is coming from different domain. This has 3 elements, this has 4 elements. So in order to apply these guys on the vector, let's make them similar, right? So how I can do that is, okay, I take a vector and maybe let's treat or transform that vector into a quaternion having a 0 scalar part. So these 3 vector parts are now coming from the vector. So that's what I have here, okay? In R3, this is the vector. So the corresponding pure quaternion is this with a 0, and this vector is same as this. Okay, so it actually has a one-to-one correspondence, meaning that, let's say I have another vector W. Okay, so that W will also have another pure quaternion here, right, with a 0. Now, if I add these 2 vectors, I will get another vector. Okay, let's call it, so I don't know, A. And interestingly, so it will correspond to certain quaternion, and that is same as adding these two guys. Okay, this and that generate that. So that's this one-to-one correspondence, right? So for each vector in three-dimensional space, there is a corresponding pure quaternion, right? The reason why we needed this is I have a vector V. I want to apply quaternion, and I have to, when I apply, I have to make both these some similar objects, right? So I made this a pure quaternion before I apply, right? So if you can remember, when we applied a rotation matrix on a vector, we got another vector, and so this acted as the rotational operator for this rotation proceeding, right? So in a similar thinking, now maybe we can assume, okay, we have the vector, let's apply Q. So let's see whether we get another vector. The first thing is we have to see whether we are getting a vector or not, right? Later we will see whether that is actually a result of like a rotation operator. Okay, V and W. So that I will come to that a little later. Let's first see whether we can get a W when we apply the quaternion on V. Okay, so now when we look at this, so I'm going to look at the answer of this QV. Okay, because we already know how to calculate the product of two quaternions by now. So this is my quaternion, which I'm apply on the vector, and I made it a pure quaternion, right? Then only I can do this whatever the multiplication, right? I have the rule, the formula here. So let's just apply and see. So this guy times this becomes 0. This q times q dot v part is here. 0 times q is there. Then we have q naught times v, and then q v cross. Okay, so this 0 guys would disappear, and we are left with this one. So you, if you carefully look at this, you can see this is a cross product. Okay, so this will give you a vector, and this is a scalar times a vector, so this is also a vector. This is a dot product. This gives me a scale. Okay, now can somebody tell me if this is giving us a vector? Okay, so we are expecting a vector out of it, right? You apply the operator on the vector, we are expecting another vector. Okay, so is there any criteria that should be satisfied by this answer if you want to get a vector out of this? Can you think about it and tell me? So this is a vector, this is a vector. So what should the answer be if we are expecting a vector out of this? Can someone try to give an answer? Okay. Vector q need to be 0. Vector q. Scalar part should be 0, so q dot v should be 0. That's great. I think that's the answer I'm actually expecting. Thank you for the answers, right? So that's correct. um, this part over here, right, should be equal to 0. So remember in the previous slide I told you for each vector I can find a corresponding pure quaternion in a quaternion space, right? So if I'm expecting a vector, there should be a corresponding pure quaternion in this particular part, right? So that, therefore, in this answer also, this has to become 0. But can that happen? I mean, now V is some arbitrary any vector, right? Because I'm talking about I'm having a vector, whatever it is, right? It is not a special vector as such, it's some vector. And I am applying a quaternion, okay? So, this case, so if the dot product needs to be 0, then this Q and V should be perpendicular or orthogonal. That is like a special scenario, right? Because that will not happen all the time. That will happen only when such special Q is chosen, right? But I should be able to choose my Q and V can be anything. Therefore, this is not giving me 0 all the time. So there is a problem in this, okay? So I thought maybe I just take the product of these two to give me a vector, but seems like it is not happening, right? So this is what is explained here. Okay, they should be orthogonal, right? We can't expect our quaternion rotation operator to uh, consider simply for single quaternion, right? Okay, now we don't stop there. We will think about whether we can make use of this quaternion to somehow get a vector output. Then the smart people came uh, with another solution. Okay, let's forget about the vector, just the simple product of the two quaternions. How about we, okay, so what I mean by that is, okay, so there is a vector I need to rotate. Okay, so I have V. I want to apply Q. Q times V did not work. Then let's think about the triple product and let's bring in another quaternion R to the picture as well. Okay, so we take, this is the quaternion and I invite another quaternion to the picture and I have the pure quaternion which I want to get rotated. Okay, so there can be 6 possible quaternion triple products. Okay, so let's say this is P is my pure quaternion and these are the two guys I introduced. Okay, so I can arrange them in different ways, right? There are 6 possible combinations: PQR, PRQ, QRP, RQP, RPQ. Okay, so if we further look into these possible combinations, you can see whenever we have Q times R, so these are the two guys, the quaternions, the general quaternions. So this would give me another quaternion, right? Q times R, this is giving me maybe another quaternion. R times Q is also giving me a quaternion. And similarly QR, RQ. So all these would resolve to a double product. So you can see this will be another quaternion, and now p times that one. Okay, again p times that one. P times this guy, P times this one. So this we already had a look at here, right? This, it didn't work, right? This just a Q times V. This did not work. The double product did not work. Therefore, all these four will not work as well because Q will give you another quaternion. So P times that whatever quaternions, right? P times the other. Okay, then we are only left with these two that we have to check. Okay, so it can be RPQ or QPR, right? So without loss of generality, maybe we can just take just a single one because Q is a quaternion, car is another quaternion. So I can just maybe later check the other one. Okay, so let's just take one and see what happens. Okay, so now what I'm going to do is I'm going to analyze QPR. Okay, let Q be Q naught Q. P is our vector. So this is a pure quaternion, right? This is the vector I want to get rotated or whatever. And this is the third one that I introduced, okay, in addition. Now that is actually strange because I have a vector V, I have Q, I want to apply it here. Now I'm inviting this another R to the picture, right? Because the QV did not work. Anyway, let's see how whether it can help us to do this rotation. So now simply I want to multiply Q, P, and R using this particular formula for two quaternions, but of course you should be able to do this, right? So when I do the multiplication of these three, again what I'm interested in is the scalar part, right? So there's a scalar part plus a vector part, right? So let's take the real part or the scalar part and I will write it here, okay? So maybe later you can verify this answer. And this is what you would get for the scalar part. Okay, and to simplify this scalar part, I will make use of vector triple product. Maybe you have learned this in some mathematics course, right? If I have A dot B cross C, that would be equal to B dot C cross A. So there is again this cyclic nature, right? A, B, C. And I can make use of this to maybe do some changes to this part, right? So you can see already QPR order has changed with the help of this. So this is from vector triple product. Okay, please search for that. Okay. So anyway, that's only for simplifying my answer. Okay, so what I need to do is, so this is my scalar part, right? So I want to make this become 0. Okay, now suppose that this R, now I introduced the R quaternion, right? So this is equal to R naught plus the vector part. So Q naught and the vector part is equal to minus Q. Okay, so I'm just telling you what if that happens, right? So if that happens, you can see this q. Okay, q dot p bar. Sorry, this one r naught equal to q naught. Okay, and here for r I can replace minus q. Okay, so these two would cancel off. And here, if r is equal to minus q, then these two becomes parallel vectors, and this cross product will be 0. So this whole thing would become 0. Okay, so what, in other words, what this means is r is r naught scale. Okay, so this you can see is equal to q conjugate. So basically what I did was, okay, there was a vector. I am applying a q quaternion. I introduced r, right? So I already told you, like, bringing this another guy into the picture is already strange, right? It's not a wise thing to do. So, but if I make this r such that it is equal to q conjugate, right, here, then no problem, right? Because now q and some related guy, q conjugate, is the one which I have actually introduced. So I'm now making use of q and q conjugate to apply on v, right? So basically my vector triple product now becomes q conjugate. Okay? So you can see by this part, it thing is becoming 0, right? Therefore, whatever the answer I get from this has a 0 scalar part plus some vector part. So this is basically a pure quaternion, and that makes us happy, right? That's what we wanted. Okay, so graphically, let me show you. There was this vector, and there is a corresponding pure quaternion, and I wanted to apply this general quaternion on this one, and I made use of the triple product, right, with the help of the conjugate, right? And the answer is also a pure quaternion because this part vanished, right? The real part vanished. Therefore, it's a pure quaternion. That means there is a corresponding vector v, sorry, w. Okay, so when q is applied on v, now I manage to get another vector. So there is only few questions left. Okay, so if the rotational operator, right, there should be some properties satisfied. Can somebody tell me if this is v, and if I apply a rotation made or whatever operator, let's say I get w. Okay, so what are the properties that w should satisfy? If I think about the magnitude of w, it should be equal to what? Should be equal to magnitude of v, right? Because we are only rotating, we are not scaling. Okay, so that's one thing. And then the other thing is this rotation should contain some maybe angle information, right? Because this is a rotation matrix, so rotation operator, there should be some angle information coming from this R. Okay, then we know that this operator, let's say now let's call it Q again, then we can safely say, okay, Q is a rotational operator, right? In this case, we only showed you that we can get a W, but we still don't know that it has the same magnitude of V. Maybe we have to check and confirm, right? We find out the norm of W, and it seems like what we did here is a rotational operation. Okay, so we will do that in the coming slide. So maybe we can move on to the second aspect, that is, can we associate an angle with a quaternion? Right? Otherwise, it's confusing for us, right? If you don't know a certain angle associated with the quaternion, we don't know how much our vector is going to get rotated, right? So let's see whether we can associate angle to the quaternion now, right? Again, we are talking about unit quaternions, right? Here. So unit quaternions, right? And if the norm of the quaternion is 1, we can write this equation. Okay, Q naught squared plus the norm of the vector part squared. So basically this was this equation we had before, right? Q3 squared. We take any angle theta, right? I'll show it here. If we take any angle theta, we know this nice equation, sine squared theta plus cos squared theta equals 1. So this is applicable for any angle theta, right? So now you see there is some uh, similarity between these two, right? Therefore, we can figure out a unique angle theta between minus pi and plus pi that satisfies this equation number 2, sine squared theta plus cos squared theta. Okay, so we can define satisfies equation. Therefore, now you can see, okay, I can maybe think about Q naught as sine theta and the magnitude of the vector part as cos theta, okay, from 1 and 2. So you can see I carefully integrated an angle into the quaternion, right? So with that, I can do one more thing. Let's define a unit vector u, this just a unit vector u in the direction of q. So there is a vector part, so in the same vector direction. So if I write it like this, q naught plus q. So if I think about this guy, there is a certain direction, and I can define a unit vector in the same direction, right, u. So that would be equal to q divided by its norm, okay? And q norm is equal to sine theta, right? Therefore, the new representation of my quaternion, which is q equals vector part. So this would be equal to cos theta. This would be equal to this guy, right? So this is u sine theta, where this is a unit vector in the same direction. Okay, so this is my new representation of the quaternion, which now includes a angle theta. Okay, right. Only we are converging, but another thing that we need to do is, okay, there is this vector v, I apply q. So when I say I apply q, it is not q times v, but instead it's q p q conjugate. That's the operator applying the quaternion, right? So what I next need to find out is, okay, I apply v and let's say I got w, whether this angle is theta or not. Okay, because now I introduce this theta, right? Now I have to check whether this angle is theta or not. If that is the case, maybe that is satisfied, right? So before that, mm, we have to check the norm also, right? I want to make sure this has the same norm as this guy. So it's pretty straightforward. So norm of q v q conjugate. Okay, so we know that the norm of the product of quaternions is equal to the product of the individual norms, right? That we showed earlier. And this is n times this guy. And remember, we confined ourselves to unit quaternions. This is 1. This is also 1. Therefore, equal to the norm of our original vector. So now the size is also okay, right? We had v, we had w, it has the same size. Okay, now the final thing is to figure out whether this theta angle is the same angle given by cos theta plus u sine theta, which is our new definition of the quarter. Okay, so let's do that as well. Maybe I skip this part and we'll do this simple example and figure that out. Okay, so instead of very complicated directions, let's just take the vector part or the unit vector part as just k. Okay, and my angle is 30 degrees. Okay, so now if I ask you to write the quaternion based on this information, you will get yeah, this one, cos theta plus k sine theta. Cos theta equals square root of 3 over 2 plus k times sine 30, which is half. Okay, so this is my quaternion. Now this is a very simple quaternion. Of course, I purposely chose a simple quaternion without having I and j parts. So all these parts are 0, just to check how much the vector is rotated by the quaternion, right? So what I'm going to do is, okay, this is the quaternion given to you. Okay, and the vector I have is, again, let's choose a very simple vector to make the calculations pretty much very simple. Again, these guys are 0 and this is just one I. Okay, so here I'm going to now apply Q on V. So W is the answer. It is equal to Q V Q conjugate. Okay. A V is just 0 plus I, because V needs to be a pure quaternion. It is minus half K. Okay, so I'm not using any quaternion product rules or formulas because that's not needed here. Because here it's a very simple vectors we are dealing with, right? So if I do this multiplication, you will see the answer is half I plus J. Okay, K times I, you get J terms, and this would be my answer. Okay, so this is basically a pure quaternion as expected. Therefore, that's no problem. But the only thing I have to make sure is, so there was V, now I got the answer W. I want to check this angle. Okay, so let's check the angle. I started with I, and I got the answer as half I plus this one. This is alpha. So can somebody quickly calculate alpha and let me know? So alpha is basically tan inverse. Yeah, this one, right? This divided by this. It's the angle. Yeah, do you remember these ones? Square root of 3, tan inverse. What's the answer? Okay, if you don't, yeah, yeah, 60, right? Pi over 3, right? Now that is somewhat interesting because if I go back, this is where I started, right? I told my quaternion had theta equals pi over 6. Okay, but when I applied this quaternion to my vector, it had actually rotated twice that amount. Something to remember, right? So quaternion Q, which has this particular representation, actually rotates twice the amount of the inherent angle. Okay, so that's something to note. So we started off with representing quaternions like this. Q was equal to Q naught, Q1, Q2, Q3. So that's one, just 4 numbers. Then we also represented this with Q naught plus Q vector. So this is like some ijk. Then we wanted to put or insert an angle information into the quaternion. Then we came up with cos theta sine theta. So that's the third way of representing a quaternion, which has the angle information. But remember, if you have angle information or the angle as theta, then this Q is actually capable of rotating our vector by twice the angle. Oh, no, that is not actually a surprise because we are, remember, using triple product, right? Q, V, Q conjugate. So it's like some sort of twice of action happen, right? Therefore, maybe it can explain why twice the angle of a rotation is happening, right? So, but you can keep that in mind. Okay. So ultimately, what this is actually that vector, and the quaternion has this unit vector part u, or else you can say it's the same direction as this hyper complex part. It's the same direction. So about this axis, this vector is rotated twice the amount. Okay, so this is like a rotation about this particular axis twice the amount. But I didn't tell you yet that the rotation is actually happening about this axis, right? I just told you, okay, twice the amount is a rotation is happening, right? Anyway, I'm not going to go into the mathematical proof of that part right now. You can later check that. So, but I will show you the diagram. Okay. Here. Okay. So you can see you have a vector v, right? And you have the quaternion q, and this is the direction of the quaternion, and this is this particular part is actually v projected into that particular axis. Okay, so basically my vector v can be given by this a projection plus the orthogonal part n. Okay, so v is actually a plus n. Okay, so in this mathematical proof, what we will show is that this a part, when undergone through the quaternion q, will remain same. That's basically correct, right? Because the axis is the same thing and a is projected on that axis, so a will not rotate, it will just remain same. So only this perpendicular or the orthogonal part n will rotate twice the amount of angle to theta to get this n. So basically the w is ultimately equal to a plus this n. Okay, because a is not rotated by the quaternion because it's the same axis, right? The same axis will not rotate. It's only the orthogonal part that will get rotated twice the amount to give you this. So the answer would be a plus n, which is this rotated vector. Okay, so you need to go through this mathematical proof later to understand the axis of rotation. So even in student feedbacks in last years, students have mentioned, don't go through all this stuff in the lecture itself because it's going to get very complicated and boring. So that's why I kept it as the last thing, and you can have a look at it. But I have two more things to tell you, which I quickly uh, share with you. So then the lecture will be complete. So the general operator formula for the quaternion I will share with you now. So what it says is, okay, there is a quaternion Q and a vector V. So when I say vector V, I'm representing it as a pure quaternion, right? Now you understand that because otherwise I can't be operating apples and oranges, so it has to be the same thing, okay? Therefore, I make it as a pure quaternion. So the general formula for uh, rotation is, so the answer is Q, V, Q conjugate, right? So this is, I need to find the answer for W, and this is basically Q naught Q times 0 plus V and Q naught minus Q. So this you have to just multiply and get the answer, but I will show you the final answer when we make use of this formula, right? I can one by one multiply them, right? So first I multiply these two and get this answer, and this is the remaining one. And I will not go to all the steps. You can little by little check this, okay? And the vector triple product will also come into play. Anyway, the final answer is this, okay? So just try to identify what is in there. So if you want to have a vector rotated using the quaternion Q, these Q parts are from the quaternion, and these V elements are coming from this vector that we need to get rotated. Okay, and you just have a certain formula, and you will get the answer for the final vector. So if you take a library, some, let's say if you are using ROS, so maybe there is eigen libraries. Likewise, you have these like inside those functions. So you just, when you call these functions, you can just get the answer, right? A certain rotation applied to a vector, you will get these answers, and inside the function you will have these steps. So basically you will have this line, okay? And also we can simplify it a little bit, because this guy is actually equal to 1 minus q naught squared, right? Because we know that these are unique quaternions. Therefore, this is equal to 1 minus q naught squared. So that we can put it here, and we have a little bit simplified equation for vector rotation using a quaternion Q. So this Q has like the three elements of the vector part. Q naught is the scalar part. Okay, so this V has three elements because this is a 3D vector, and you will get some answer ABC, right? In X, Y, Z directions. That's the vector. Okay, that's one thing. And another thing I want to show you is the connection between the quaternions and the matrices, because definitely a quaternion Q should have a connection to the rotation matrix, because they basically do the same thing ultimately, right? We uh, apply R to V and get W, or else? We apply Q to B in this manner, in a special manner, using the triple product. And again, we are getting the same W. So therefore, this R and Q are somewhat related. So again, such mathematical libraries will have, okay, quaternion true matrix. That kind of a function should be there. And there should be another function, maybe rotation matrix to quaternion, right? We have a look at that back and forth, and then I think we'll be done for this lecture. So this is the product that we have for the triple product to get a rotated vector, and I told you the general formula for that. Okay, so if I expand these three terms, okay, one by one, if I expand it, first guy, this one, okay, so here is V has V1, V2, V3, okay, and this is just a scalar, but I can write that scalar in a special way like this, like a diagonal matrix. It's the same value I put in the diagram, right? It's looking somewhat fancy, but it is how I'm going to show the relationship between this Q and the final rotation matrix. Okay, so this first term, V is V1, V2, V3, and this scalar term, I just put in the diagonal the same. So that this is my equation 1. Then if I look at this guy, okay, that again I can write it like this. So I have 2. This is the dot product. V1, Q1, V2, Q2, V3, Q3. And then I have the vector part of the quaternion Q1, Q2, Q3. And write down the 3 lines like this. Okay, 2, V1, Q1, Q1. Likewise, I can have these 3 lines. Just I multiply this guy with this. After multiplying, I can extract V1 again like this. Okay, if I extract those V1, V2, V3, I will have some remainder in this particular matrix. Similar to this guy, I will have another part for that matrix, which I now call as 2. Next, if I move on to the third part, I'm going to do the same thing. I will just take this cross product, okay, 2 Q naught, ijk, Q1, Q2, Q3, V1, V2, V3. Ultimate goal is to again have a vector V1, V2, V3 at the back. Okay, so this I will write down the cross product is, and from the product is related to the skew symmetric matrices, right? Therefore, I am going to put this into a skew symmetric matrix, right? And this V1, V2, V3 terms separate, right? So this is a trick that I'm doing. So anyway, you know that Q cross V is equal to SQV, right? We learned this in IMU theory part. This is like that operator for the skew symmetric matrix. I take these elements and put like, so here we have Q1 minus Q2 and Q3 part. And this 2Q0 comes from this, right? Every term is multiplied by that. Okay, so this is that, and V is this one. So the skew symmetric matrix part is also there, and I created this third. Now I have 3 equations. This one, this one, and this one. All three has these guy v1, v2, v3 at the back, right? So I can again take all together, put all these three equations together and take out v1, v2, v3, and basically I'm just adding this element, this and this 0 to create the first table. Right? So I just add all these to create this huge matrix times v1, v2, v3. So this is like some matrix times v, right? V is the vector I wanted to rotate. Basically, this is equal to some, it's like some rotation matrix time v. Okay, so how do I create the rotation matrix? I take the quaternion and individually take these elements q1, q0, q1, q2, q3. So I know all these elements, right? The four elements I know. And I create these 9 entries in the matrix, and that gives me the rotation matrix. So that's the connection between the rotation matrix and these entries in the quaternion. Okay, so I can go back and forth from quaternion to rotation matrix. Right. So with that, we can conclude the quaternions lecture, and let me summarize quickly what we learned, right? So I told you the motivation, how we came up with the quaternion. So for the complex, we started with the complex numbers, and we saw that using a complex number, we could rotate a vector in a planar surface, right? In 2D. Therefore, Sir Hamilton came up with hypercomplex numbers. So that's like three-dimensional complex numbers, and made use of that to do three-dimensional rotations. That gives us the quaternions. And then we just gave some rules how to tackle with the quaternions. And finally, we looked at graphically the meaning of quaternion and how it can actually do a rotation. Okay, and at the end, we looked at how we can create the rotation matrix from a quaternion. So that connection also was established. And I didn't go through the mathematical proof, but I told you the idea. So please go through it to get an understanding, right? How you can actually prove that the quaternion in fact rotates about the vector part twice the inherent angle. Okay, right. So thank you very much for your attention, and that concludes today's lecture.